So let's look at some examples and try to see how we calculate this one-sided limit. So let's start with a function that is defined by x squared plus 2 if x is less than 2, takes a value 5 at x equal 2, and is defined by 4x minus 3 if x is greater than 2. And let's say we're interested in knowing whether this function has a limit at x equal 2, and if it does, what this limit is. The function is defined by different expressions on the left and on the right of x equal 2. Therefore, to investigate the limit at 2, it makes sense to first look at what's happening from the left and what's happening from the right. When x is approaching 2 from the left, x is less than 2 and therefore coincides with x squared plus 2. Therefore, the limit at 2 from the left is the same as the limit of x squared plus 2 at 2 from the left. But we know that for a polynomial, to get the limit at a certain value, we only need to plug in the value. So we plug x equal to in x squared plus 2, and we get 2 squared is 4 plus 2, 6. On the other hand, from the right, when x is greater than 2, the function f coincides with the function 4x minus 3. This is again polynomial, and to get the limit at 2, we just plug x equal to and get 8 minus 3, 5. We obtain a different value from the left and from the right, and therefore the limit in the usual sense at x equal to does not exist. Let's consider a second example. Function f is defined by square root of x plus 3 when x is less than or equal to 1, defined by x squared plus 1 between 1 and 3, and by 2x plus 1 when x is greater or equal to 3. What is the limit of this function when x is approaching 1? Once again, the function is defined by different expressions, whether we look at x less than 1 or x greater than 1. Therefore, we're going to first look at the one-sided limits at 1. From the left, when x is less than 1, the function coincides with the function root of x plus 3. When x is approaching 1, x plus 3 is approaching 4, and therefore root of x plus 3 is approaching 2. On the other hand, from the right, when x is greater than 1, f coincides with the function x squared plus 1. Remember that we're looking at the limit at 1 from the right. That means x is greater than 1, but close to 1. If it's close to 1, it is in particular less than 3, or at least we can assume that x is less than 3. And so the limit when x is approaching 1, whether from the left and from the right, for x squared plus 1, is the value of x squared plus 1 at 1, which is 2. We obtain the same limit at 1 from the left and from the right, and therefore this common one-sided limit is indeed the regular limit, and f has a limit at 1, which is 2. Let's consider the same function and look at the limit of that function at x equal 2 this time. The limit of a function at a certain value depends on the values of that function on some small open interval centered at that point. Note that here the function f coincides with the polynomial function x squared plus 1 on the open interval 1, 3, in particular on some small open interval around 2, the function is the same as x squared plus 1. That means that the limit at 2 of f of x is the same as the limit at 2 of x squared plus 1, which is obtained by plugging x equal 2 in this expression, and gives us the value 5 for the limit of f at 2. So you see that even though the function is defined piecewise, there is no need for the use of one-sided limits in that case, where the function is defined by a unique expression on some small interval around the point. On the other hand, if we look at the limit of f of x at 3, you see that the function is defined by different expressions, whether x is less than 3 or x is greater than 3. Therefore, we need again to use one-sided limits. At 3 from the left, when x is less than 3, f of x coincides with the function x squared plus 1, and therefore the limit is the limit of x squared plus 1 at 3, which is 10. From the right, when x is greater than 3, the function coincides with 2x plus 1, and therefore its limit at 3 is the value of 2x plus 1 at 3, which is 7. We find different one-sided limits at 3, and therefore the limit of f of x at 3 in the usual sense does not exist. Let's look now at a different kind of example. The limit at 2 of absolute value of x minus 2 over x squared plus x minus 6. The first thing we would do is try to plug x equal to in this function. At the top we get absolute value of 0, which is 0. At the bottom we get 4 plus 2, 6 minus 6, 0. So we have an undetermined form of the type 0 over 0, and we need to lift the indetermination. The problem is we don't have a quotient of polynomials because of the absolute value. We would if we could drop the absolute value, but the absolute value is there. So what can we do? The problem is, what do we do with this absolute value? In other words, what is really the absolute value of an expression? Well, when I ask this question in my regular classes, usually I get the answer that it is a distance between A and the origin on the real line. This is perfectly correct. However, for the purpose of calculating this kind of limit, we would like a more algebraic interpretation of this fact. So what is absolute value of A? How can we interpret that? Let's look at some basic examples. Absolute value of 5, of course, is 5. Absolute value of negative 5 is 5. In other words, when you take the absolute value of something, if this something is already positive, you don't change anything. And if it is negative, well, you make it positive. How do you make it positive? You take its opposite, and the opposite of the negative number is going to be positive. In other words, absolute value of A is A if A is already positive or 0, and negative A if A is negative. That makes negative A positive, of course. So here in the expression whose limit we are trying to determine, the absolute value of x minus 2 is going to be x minus 2 if x minus 2 is positive, in other words, if x is greater or equal to 2. On the other hand, it's going to be the opposite of x minus 2, if x is less than 2, right, when x minus 2 is negative. Now, how can we use that to obtain this limit? Well, you see that the condition to rewrite absolute value of x minus 2 as either x minus 2 or negative x minus 2 depends on whether x is greater or less than 2. So that means we have to use one-sided limits at 2. So what happens from the left? When x is approaching 2 from the left, x is less than 2. We just have seen that if x is less than 2, x minus 2 is negative, and therefore absolute value of x minus 2 can be replaced by negative x minus 2. Now we obtain a quotient of two polynomials which are both 0 at 2. We know what that means, we've seen that before. All we need to do is factor x minus 2 at the top and at the bottom. We know that it's possible because both top and bottom are 0 at 2. At the top it's already done. At the bottom here is the factorization, and now we know that we don't change the limit at 2 if we cancel the common factor x minus 2. So we get the limit at 2 of negative 1 over x plus 3. This is a rational function that has 2 in its domain, so we can just plug x equal to in this to get the limit, which is negative 1/5. So the limit from the left at 2 of our expression is negative 1/5. From the right, x is approaching 2 and is greater than 2 If x is greater than 2, x minus 2 is positive, and therefore absolute value of x minus 2 is x minus 2 itself. Again, we end up with a quotient of two polynomials that are both 0 at 2. So we have a common factor x minus 2, and after cancellation we obtain the limit at 2 of 1 over x plus 3, which is 1/5. You see that we find 1/5 from the right, negative 1/5 from the left, so different one-sided limits. If we have different one-sided limits, then the regular limit at 2 does not exist.